In this video, I want to continue with our application problems in differential equations. In particular, we're going to be talking about mixing problems here. So if a single compartment contains a certain concentration of a pollutant, then the rate of change of a pollutant per unit time is equal to the rate in of that pollutant minus the rate out of that pollutant. If we denote the amount of pollutant at the tank at time t as x of t, then the rate of change of the pollutant is x prime of t, or dx dt, however you want, whichever notation we want to use. Okay, so let's try to solve this question here. Take a moment to read through this, and once you've done that, continue on. All right. So we have the question here wants to know, we want to find the time it will take to increase the salt concentration in the tank to 1 gram per liter. So we need to come up with some differential equation. Well, we use this formula up here. Right? The rate of change of pollutant per unit time is equal to rate in minus rate out. When x of t, again, is the amount of pollutant in the water at time t. So this gives us x prime of t is equal to rate in minus rate out. Now we need to figure out what rate in and rate out are. Well, rate in is the concentration in times the flow rate of the water. So the concentration of the pollutant times the flow rate of water is the rate in. Well, what is that? The concentration of the pollutant in the water that is going into the fish tank is 3 grams per liter. The rate of the water in is 2 liters per minute. Okay, rate out is again the, by the way, where did we see that? 3 grams per liter is here. And 2 liters per minute is allowed to run into the tank at a rate of 2 liters per minute. Okay. So what about the rate out? Well, we say that the mixture is thoroughly stirred. What does that mean? That means we assume that it's all instantly stirred. And so what is the concentration of the mixture that is going out? Well, the concentration is the amount of pollutant in the tank. Hey, that was x of t. Divided by the volume of the tank. Well, that is 150, which we're given in the problem. And this is grams per liter. Okay. And then we multiply that by the rate of the water leaving the tank, which we said the rate out was the same as the rate in, so it was also 2 liters per minute. Okay, so this is our formula here. X prime of t is equal to 6 minus 2 over 150, which is reduced to 1 over 75, times x of t. So that right there is our equation. All right, that was supposed to read rate out. That right there is our equation for this problem. Okay, so what do we want to do? Well, as with most of these differential equations problems, or all of these differential equations problems, you want to solve for x of t, but you do that in with certain methods. Notice that this is both a linear equation and a separable equation. Let's go ahead and treat it like a linear equation for this problem, which means we're going to use our method of integrating factor. So let's do that. So we had x prime of t. Let's make sure that that's readable for everybody. X prime of t. And then we want to add over the 1 over 75 x of t. And this is equal to 6. So now this looks like our linear equation, our first order linear equation, in which case our integrating factor is mu of t is equal to e raised to the integral of p of t, but p of t is 1 over 75. The integral of that is t over 75. Okay, then we multiply that on both sides of the equation, and the left-hand side becomes the derivative of the product, the integrating factor, times x, and that's our left side. And then the right side is just 6e to the t over 75. Okay. Now we need to integrate both sides. Well, the left-hand side just becomes e to the t over 75 times x. The right-hand side, so that is the integral of 6e to the t over 75. Well, if you do that whole calculation, you should get 450 e to the 1 over 75 t, so t over 75, plus some constant c. All right, we divide by e raised to the t over 75 on both sides, and we get x is equal to 450 plus c over, actually, let's just write this as c times e to the negative t over 75. All right. So now what do we need to do? We need to solve for c. How do we do that? Well, we have the initial condition, x of 0 is equal to 20. So just plug in t is 0 and x is 20. So we get 20 is equal to 450 plus c. Then e raised to the negative 0 over 75 is just 1. So this is 20 is equal to 450 plus c, or in other words, c is equal to negative 430. Okay. Well, what does that do? That gives us the equation. X is equal to 450 minus 430 e to the negative t over 75. And that's our differential equation. Unfortunately, that's not quite the end of the problem because the question asks us to do a little bit more than that. It says, find the time it will take to increase the salt concentration in the tank to 1 gram per liter. What does that mean? If we want the concentration to be 1 gram per liter, well, that says that 1 is equal to the concentration, which is x of t, that's our function that we just calculated, divided by the amount of water in the tank, because that's how you get a concentration, right? It's the amount of pollutant divided by the total amount of liquid in the tank. So the amount of the pollutant is x of t, and the amount of water is 150. So we do that, and we get that this is 3 minus 430 over 150 e to the negative t over 75. Subtract 3 on both sides, multiply by negative 1, so that you get 2 is equal to 430 over 150 times e to the negative t over 75. Move over the 430 over 150 by dividing by that, and then take the natural log of both sides and all of that, and solve for t. Once you do all of that, you should end up with negative 75 natural log of 30 over 43. Sorry, I'm supposed to say 30. Is equal to t, which is approximately 27 minutes. All right. So that was our first problem. Yeah, one more example like that. But now we are going to do the similar problem, except we're asking how long would it take if we could increase the flow rate in of the water to 2.5 liters per minute, but the flow rate out stayed 2 liters per minute. Well, we're going to have to change our equation now to dx dt, or x prime of t, is equal to, still 3 is the concentration. The flow rate in is now 2.5 liters per minute, minus, okay, now this part changes as well. The concentration is the amount of pollutant divided by the volume of the tank. Unfortunately, the volume of the tank is now changing. And how is that changing? Well, let's use V of t to write out the volume of the tank. So V of t, well, we're putting 2.5 liters into the tank per minute, but 2 liters is leaving the tank each minute. So what does that mean? That means we started with 150 and we are adding 1/2 of a liter per minute. So 150 plus 1/2 t. And that would be our equation for the volume and how that is changing with respect to time. So this right here, this is your concentration out. Again, that is the amount of solvent in the tank, which is x, that's how we defined our function x, divided by the size or the amount of volume in the tank at time t. And then we multiply that by the flow rate out. The flow rate out remained at 2 for this particular problem. Okay, so here's our new equation. This time we notice that it is still linear, but is no longer separable. So let's again use the method of the integrating factor. All right, to do that, we need to rewrite this. This is x prime of t plus, all right, 2 over 150 plus 1/2 t times x is equal to 3 times 2.5 is 7.5. Just to make this a little easier to work with, if you multiply this term right here by 2 over 2, this becomes 4 over 300 plus t, and then times x is equal to 7.5. We just did that to get rid of the fraction in that denominator and make this a little bit easier to deal with and write out. You could have kept it as is, though. All right, so here's our differential equation. I want you to take the time to solve that. So pause this right now and solve this, find the integrating factor, and then solve that equation. All right, and now that you've done that and you've unpaused this, you should end up getting that x is equal to 1.5 times 300 plus t plus c over 300 plus t raised to the 4th power. All right. And once we solve that, Our initial condition was 20 grams of pollutant at time t equals 0. So 20 is equal to 1.5 times 300 plus C over 300 plus 0 raised to the fourth. Plugging all that in, we end up with C is equal to negative 430 times 300 raised to the fourth. Okay. So we write all that out and we get X is equal to 1.5, 300 plus T minus 430 times 300 raised to the fourth, all divided by 300 plus T raised to the fourth power. And here's our differential equation. Well, once we do that, what do we want to do? We wanted to again determine the time it would take to increase the salt concentration to 1 gram per liter. So again, this is 1 is equal to X over the volume. Well, that is this equation up here. I'm going to leave that as X, so I don't have to rewrite all that again. Over our volume equation, well, our volume equation was 150 plus 1/2 T. Okay, so what you should do here is plug in yeah, okay. So this is, again, we can multiply by 2 over 2. So we end up with 2 over 300 plus T times X of T. All right. Then plug in what X of T is here and solve for T. Once you do that, you end up with T is approximately 22.397. And that ends our video on the mixing problems.